I'll still be talking about the same topic, so thank you everyone for still bearing with me. And so I tried to give you a way last time to relate Haley-type theorems and some notion of topological complexity, right? So you have a family of sets in RD, and you look at how complicated the intersection of subsets can be. Complicated measured in terms of type of intersection, number of connected components, and complexity of those components. And so again, what it's about is those Haley-type theorems, right? Bounding the size of inclusion minimal intersection subset of with empty intersection. And the goal is to get some common topological explanation to many Haley-type theorems that exist. So what we covered on Friday was how you can analyze this problem through nerve complexes, right? So essentially proving a Haley-type theorem when you look at the intersection hypergraph, which is a nerve, means to prove that you don't have certain holes, okay, particular holes, the boundary of a simplex. And so we went to look at more general holes, and we saw that there was this nerve theorem that allow to relate the holes that you have in the nerve to the holes that you have in the union. And so we could say that because your sets are living in RD and they're nice, say they're open, then the union cannot have arbitrary many holes. So that's a standard approach, and we saw how we can actually push it a bit further involving some projection theorem. And what I'd like to talk today is a... Yes? Okay. If there are any questions, you don't hesitate to interrupt, definitely. So what I'd like to talk today is a different take on the same topic. So rather than look at the nerve and try to use something like the nerve theorem to prove Haley-type theorem, we're going to use embedding, and more precisely, lack of embedding, non-embeddability. So it will have a flavor more closer to the first talk I gave last Wednesday. And the ingredient we will use is, well, a general principle to get Haley-type theorem from non-embeddability, some application of Ramsey theory to find non-embeddable structure, and also a bit of homological algebra. Okay? So again, when you take a simplicial complex, an embedding is a drawing of that complex. Okay? So you map singleton to points, H to arcs, and so on. And as I mentioned already, you can get various types of embedding. You get the linear embeddings where everything is straight. You get the PL embedding where you allow to decompose and have piecewise linear parts. And then you get the topological embedding where wide curve, as long as it's continuous, it's allowed. Okay? And if you look for, and the jump from these, so there are many theorems in discrete geometry that you can see as statements about embeddings, about linear embeddings. Okay? Properties of convexity can be sometimes understood as properties of linear embeddings. And there's a very active line of research that asks, okay, when you take those theorems, you formulate them as existence or non-existence of linear embeddings, what happens when you go to topological embeddings? So one example is Radon's theorem. Maybe some of you know it. It just tells you that if you take 4 points in the plane, you always have a way to partition them into two parts so that the convex all intersect. Okay, your 4 points, they could be like this, and then your partitions will be this, or they could be like that. Okay, and then you have a partition that is this, and a part that is this, and another part that is that. And one way to state this is that you cannot embed, and of course if you go to higher dimension, so it's 4 points in the plane, 5 points in 3D, and so on. One way to phrase it is, if you take the boundary of the simplex with 4 vertices, and you try to map it in the plane linearly, there will be 2 faces with no vertex in common, but their image will intersect. Okay? So it's a statement about the non-existence of a linear embedding. Okay? And this So there is a very standard proof of Helly's theorem for convex sets from Radon's theorem. Okay, and this proof starts by saying, assume that you have convex sets. Okay, and so assume you have k of them. They are in Rd, so that any d plus 2 intersect. Okay, so we want to prove that they all intersect. Okay, so that's sorry, any d plus 1 intersect. So any proper subset intersect. Whenever you drop a set, you know that they intersect. And because we have at least d plus 2, we want to get the conclusion of Helly's theorem, meaning you must have a point common to the whole intersection. So one way to go on is to just, for every set, J, I'm going to pick a point that misses at most AJ. Okay, so these are my 4 points. Now, I apply Radon's lemma. It tells me there's a partition, and you can check that the point common in this partition, so this guy can only miss the red guy, this guy can only miss the blue guy, so anybody on this segment can only miss the red and blue guy, anybody on this segment can only meet the green and yellow guy, so this guy can meet nobody. Can miss nobody. Okay? And this proof structure only uses embedding properties, right? So what I could do is, once I picked those points, I could extend this linearly into a map of the boundary of the simplex into Rd, and because that complex does not embed, I get two faces that intersect. Okay, I'm just reformulating it this way. But when I see it this way, that means that whenever I get a non-embeddability result, I should be able to get some kind of Helly type theorem. So let's try with K5. So K5, you cannot draw it in the plane. Okay, there will be faces that intersect. So one way to use it, so if you use it this way, what you will be able to prove is that if you take a family of sets where intersections are connected or empty, so when sets intersect, you have a family of sets in the plane, and when they intersect, the intersection is path connected. So in that case, I will be able to apply this drawing argument, okay? And I will be able to prove that there is some Helly bond. The way I do that is, so I'm starting with this family here, I pick my points, okay? Yeah, again, each point misses at most one set. And now I connect them. Okay, and I know that as soon as I connect all pairs among 5, 2 edges will intersect. Those 2 edges will have no vertex in common. Okay, so, and because the intersection is path connected, whenever I pick 2 points, I can connect them inside the intersection of everybody but those 2 guys. Okay, since those edges, so that means that points here on this path will miss possibly distinct sets on points on this path. So again, this guy is in everybody. Okay for everyone? Yep. Okay. So, and you can play this game with every non-embeddability result that you find. And they give you different type of Helly type theorems. Okay? And you get different bound on the Helly number, but you get also different assumption, stronger or weaker, depending on what you want to try to embed. So there are 2 natural examples. One is Radon. So there is a topological version of Radon. Okay. And what it assumes on the intersection is that they're contractible, so that you can actually draw inside. And the bound you get on the Helly number will be d plus 1. And you can also use the obstruction result I mentioned last time, the Van Kampen-Flores theorem, and then you will need to draw complexes of lower dimension than Radon. So if you want to apply in Rd, Radon will ask you to build faces up to dimension d, or d minus 1. Okay? This will only ask you to build faces up to dimension d half. So the connectivity that you will require in the intersection to be able to connect your dots and to fill the triangles and so on will be smaller. Of course, you have to pay a price for this. It's that the number, the Helly number, is larger. Okay? And the question that we worked on with my colleagues is whether we could allow some disconnection, but some controlled disconnection. Okay? For example, what happens if we allow sets to have 2 connected components? So then if I try to play this game, say I pick a point here that misses only the green guy, and a point here that misses only the red guy, then they are both inside the blue guy, but they might end up in distinct connected components. So I cannot connect them inside the blue guy. Okay, so what can we do? And this is another example showing, okay, maybe I could draw 5 points inside some intersection, and the intersection has the shape of a ring. Okay, and maybe I could connect any 2 points among those 5 points inside this ring. But it's possible that I can fill no triangle. If you look at this drawing, choose any 3 points, look at the triangle they make, it will wrap around the hole. So you can never fill a triangle in such a thing, in such a situation. Okay, so is there something we could do with that? And the answer is yes, there's something we can do with that. And the first ingredient will be to use Ramsey to find non-embeddable structures. Okay, so everybody knows Ramsey theorem? Yeah, okay, so I'm going to use a hypergraph version. The only thing we care, so I will never care about what the Ramsey number is. Never, ever. Okay, just finite. So if you give me a hypergraph, all hyperedges have a certain size, it's constant. Okay, number of vertices is large, arbitrarily large. Okay, but the size of the hyperedges is constant, and I color them with a constant number of colors, and I'm looking for a uniform subset of a constant size, and I know that this will exist as soon as I have enough vertices in my graph. Okay? And using this, what you can argue is that if you take a graph on n vertices where any 3 span at least one edge, then you must have K5 somewhere if you have enough vertices. It's obvious? Okay, no topology, just graph theory. In fact,
well, you can't have you can't have 3 empty sets, so yeah, sure, you should have a K5.
Okay, so one way to prove it is just numbers of vertices. Okay, and you know that every time you take 3, there are 2 that you can connect. So
it should be 2, 3, 9, no?
I just want to prove this. I'm not saying it's optimal. I'm not saying it's the simplest, because I'm going to do something else with this argument.
Oh, okay.
Okay? So now, whenever I take 3 integers, say 1, 10, and 25, I know that some of them can be connected. 2 of them. So I only have 3 choices. Either I connect the first and the second and the third, or the first and the third. So I'm going to label every triple by which choice I can make. So it could be that I have a triangle, so all 3 choices work. I pick anything I want. Okay? So I color every triple by some pair, so that the ordering, when I take that pair, I can connect them. So in this graph, this is some example of choices of labels. Now, this is the coloring of the complete 3 uniform hypergraph. I can apply Ramsey, and then I know that there are some 9 vertices that span triples, all colored by the same pair. Okay? And so I number these vertices from 1 to 9. Okay? And if my pair is 1, 2, then I can take those guys to span a K5. If it's 2, 3, I can take those guys. And so on. The idea is just, I can always...
Sorry, but how can, if for some 3 points,
yes?
if there are many 3 edges, for example, then how can we...
I choose freely.
Yeah.
Any choice is correct.
Any choice is correct.
Yes. Okay? It will just give me a different coloring, but Ramsey's theorem applies to any coloring. Okay? And the only thing I need is to be able to squeeze. So here, when I take those guys, I can, if I want to draw the edge between, I can draw an edge between 1 and 3 because I can squeeze 2 here. Okay, I can draw an edge between 3 and 5 because I can squeeze 4 here. Okay, so when my monochromatic set is colored by 1, 3, I would take these guys. Okay? So exercise prove a better bound, what can be done. What I'm interested in is that this is a systematic argument. So I can replace any 3 span at least 1 vertex by any 10, any 20, it will still be fine. I will get a different bound, but it exists. And using this, I can prove a Helly type theorem. Okay? Because, so now what I'm going to, remember we just proved that from non-planarity of K5, you get that if a family of subsets of the plane has path-connected intersections, then the Helly number is at most 4. Now I'm going to relax the assumption, rather than asking that it has path-connected intersection, I'm going to ask that the intersection have at most 2 connected components. Okay, so I will have the same type of assumption on the graph I can draw. I'm going to, again, pick the points, pick a point missing every set. Among any 3 points, 2 can be connected in the intersection of the other set. Okay, so I connect those. I just drew a graph which has the property that among any 3 vertices, there is some edge. So that means that if my graph has more than this many vertices, at least this many vertices, there will be a K5, so there will be 2 edges that cross. Okay, and that will tell me that the intersection is non-empty. Everybody is okay? Because I lied to you, so.
It doesn't work.
No. First person to point out a flaw there, get some chocolate. I get some nice chocolate in my office. There's a small gap.
It should be +1, not -1.
No.
You mean the chocolate?
Nope.
Okay.
So why does the intersection point tell you that the intersection of everything is non-empty? Okay, I find 2 edges, I know they cross. And I'm claiming this intersection point is a witness that the entire family has an empty intersection. It's because every edge has to lie in some subset here. Okay, so I know I can find 2 different edges, 2 independent edges, with no vertex in common that cross. So previously, each edge was drawn in the intersection of I different from A and B, when I draw an edge between PA and PB. Now I have to use a dummy guy, C, to tell me that I can connect PA and PB. So it could be that the 2 edges that intersect, they use the same dummy guy. And that means the edges are allowed to be drawn outside of this dummy guy. Okay? So it could be that the 2 edges, AB and UV, are both inside this, and they both miss C. So this can be gotten rid of by a simple trick. Now, I'm going to find an injection of this into, okay. What I'm going to do is I can just refine this argument and ensure that not only I can label, so I can label the vertices and label the edges and map this into my set in a way that is suitable for finding those intersections. Okay? So, what I mean here is you give me A and B. Say, this is first and second position or first and third position. I can always map, so I will need to label 5 vertices and 10 edges. So that's 15 labels. Okay? I can always map those 15 labels into the integer from 1 to 15 in a way that when I take this triple, IU, IV, IUV, the IU and IV are in position A and B when I consider those ordered. Okay? And the way you do that is you start by labeling the vertices here, then you add fractional labels on the edges, then you rescale everything. Okay? You just map everything back to integers by increasing map. Okay? And once I've done this, then the integers, I can use this map here to map the 5 vertices and the 10 edges to indexes in my homogeneous set. Okay? And now I'm sure that every edge uses a different dummy set and the conclusion works. Was that a bit quick? Perhaps.
So all you had to do was increase 9 to 15.
Yeah.
Then you can.
Yeah. So I just, in my homogeneous set, I just allow some room for labeling the edges. Okay, and you can always map this monotonically. The constraint of ordering on being A in position A and B can always be satisfied. Okay? Okay, so how do we continue from here? Well, what we want to do is to use this in higher dimension. So right now I was doing this in the plane, so I allowed to have several path connected components. With this, you can, of course, as soon as you drew the skeleton, you can try to fill holes, assuming sufficient connectivity. So in particular, what you get is this result of Matuszek. This is his proof. Okay, that's the way he proves it. If you have a family of sets, so that the intersection of every subfamily has at most R connected component, bonded number, then on each D over 2 connected, then the Haley number is bounded by some function. This function, you will use some Ramsey bound, of course, right? Because as we just saw. But the only thing you need to be able to do is to draw a sufficiently large complete graph. And then, because the intersections are sufficiently connected, every triangle you can fill. And once you fill 4 triangles, you can fill the tetrahedron, and so on and so forth. Okay, you just need to be sufficiently connected so that you go up to those dimensions. And once you've done that, you can draw the Van Kampen-Flores complex, right? This one, and get some intersection. And if you do so in a way where every time you fill a face, you're assigning to that face some dummy vertices some dummy sets that are different, then the intersection of the faces of that drawing of that complex will prove that the intersection of the family is non-empty. Okay, it's just the same idea. Now, we really here use the fact that as soon as you drew the complete graph, you can fill. So next thing we would want to do is allow, say, in the intersection to have some number of holes, maybe bounded. Okay, and to do that, it will be convenient to start talking about homology. Okay, so if you're not too familiar with homology, this is just a quick primer. So what we work on is essentially a vector space spanned by the simplices. Okay, so you take your set of simplices, and each of them is a different dimension. So you look at the vector space spanned by your simplices. A different way to talk about it is just you look at the formal sum of simplices of your complex, weighted by coefficients. Okay, that's this is a chain complex. What we want is to add some operators, some linear operators here that satisfies this condition. Okay, it's called a boundary operator. And then we're going to look at a chain map, which is a way to map your complex so that commutes with the boundary. Okay, so everything is fairly combinatorial so far. And in fact, a way to draw, so there's a standard chain complex here, singular chain complex, consisting of all simplices in RD. Okay, geometric simplices. And taking a realization is a way to basically send your complex K, the chain map. So you can try to draw the complex, or you can actually decide, instead of drawing every singleton in your complex by a point, maybe you could draw it as a sum of 10 points or 11 points. 11 is better. Okay, and then maybe this is the image of a point, and maybe you want the image of another point to be this, and then the image of the edge between those 2 points in your complex could be the sum of those three edges. Okay, going to chain maps will allow you to do that. So to consider embedding in a more relaxed way. Does that make sense? Okay. The only thing I care is that when I look at the boundary of an edge, what I get is so the boundary of the image is the image of the boundary. That's what I want. Okay? So then the question is, what are the coefficients we put? On what field do we take this vector space? Usually it's convenient to take Z2 in our case, because it's very discrete, it's very simple, okay, and everything boils down to parity arguments. Okay. And so when we draw graph or when we embed simplicial complexes, usually we care that the images are proper, they don't have self-intersection. When we take these things, those chain maps, we will care about something analogous. It's this criterion. Okay? We will want that when we take two disjoint simplices in K and we look at their maps, it gives us something that is disjoint. So the support of the image should be disjoint. Now, if you're trying to draw K5, right, maybe this gives you some more freedom, because maybe I get 3 vertices. So the image of one vertex is this, the image of the other vertex is that. And so I can use, if I use this as an edge, it's valid. But I could also use this one as an edge. Okay, so this, for example, when you're trying to embed without intersection, seems to give you more freedom. Okay, you can map every point to several points, and then you're free to choose any of those points as a way to draw edges. And surprisingly, it turns out this does not allow you to draw more complicated complexes, substantially more complicated. Okay, and in particular, the Radon and Van Kampen-Flores theorem, they are still valid for this type of drawing. Okay, there's no way to define chain maps from those complexes, this one and this one, into RD. Okay, so that's good. And so this is not obvious. Basically, one thing you can do, and that's what we did, is essentially go through the proof of the Van Kampen-Flores theorem and understand that the obstruction that prevents you from, that allows you to say that this complex doesn't embed, this obstruction is essentially homology. And essentially it applies already to any chain map here, not just to those that come from maps.
So
yes?
Topological embedding has any difference with homological almost embedding?
Yes.
Yes.
So when you have a map, then you're sending every vertex to a vertex.
Yes.
Okay, so this gives you a chain map.
Yes.
So it gives you, if you start with an embedding, you will get a homological almost embedding. But the other way is not true. There are some homological almost embeddings that are not chain maps. For example, if the image of a vertex is the sum of 3 vertices.
So there are homological almost embeddings
that
are not topological.
Yes.
Mm-hmm.
Yes. Because simply what you do is you map so you're mapping to vector spaces. Okay? So, and your vector spaces are given with certain bases. So essentially an embedding maps a vector basis, a basis vector to another basis vector.
Yes.
And an homological almost embedding maps a basis vector to a vector. You see, not necessarily a basis vector. So, because in your complex, the basis vector corresponds to, in your chain complex, the basis vector corresponds to the simplices. And so here we allow to map a simplex to a sum of simplices. Okay? So, now, why do we care about that? Okay? The reason is, so first,
So it's trivial that if there's no homological embedding, then there is no topological.
Yes,
this is
it's stronger.
Yeah.
Saying this is formally stronger than the Van Kampen-Flores and Radon theorem. It implies them. Okay. And so, of course, what we did before, essentially in homotopy, because we were drawing paths, we were connecting vertices, we can also make it purely in homology, right? So simply by building chain maps. And the argument will be, instead of assuming that your set is connected, you will assume that the homology is trivial. And when you have that the homology is trivial, that will help you to build a chain map, simply because, for example, you will start with this, okay, and you will define the image of the jth vertex to be a point, this point. And now, when you take the image of, you want the image of a boundary to be this, right? I mean, the image of the boundary is this by definition. And since this intersection has trivial homology, this, which is a cycle, must be a boundary. So there must be something whose boundary is this. And I define the image of the edge UV to be that something. Okay? So I can just build my chain map like I was fleshing out my embedding of complex. I'm not doing anything different. It's just a different, slightly different language. Okay? So what this will be good for is that in homology, you get cancellations. You get a vector structure. So if you give me two chains that are, I'm doing Z2 homology, if you give me two chains that are equal, that have the same homology, their sum is 0. Their sum is homologically trivial, so their sum is a boundary. And this is all about finding boundaries, right? Finding things that are boundaries. And so let's come back to this issue, right? So this is an annulus, and I drew K5 in a way that no triangle can be filled. No triangle is a boundary, okay? Because every triangle goes around the hole. Okay? So, but of course you get cycles that can be filled, right? So if you go from here to here, from here to here, from here to here, and from here to here, you should go like this. So you will avoid. So no triangle can be filled, but some quadrilateral can be filled. Okay? And this is obvious in homology, because if you take any four vertices and you look at the boundary of these two, they sum up to this. This is the boundary of a four cycle. Now in this annulus, you only have two homology class, right? Mod 2. So that means that one of these three has to be trivial. Okay, so we will, so again, this is true also in homotopy, but it's easier to see it in homology. And one way to fill holes more systematically will be to use this in combination with barycentric subdivision. And more precisely, what we can prove is that if you give me any chain map, F, okay, and you want, so I'm given a chain map, and I want to build another chain map from G to K, from G, which is Ks, into Kn, so when I compose here, so I look at any triangle in Ks, and I look at its image through G and then through F. And I want this composition to be fillable, okay, to be a boundary. So this can always be done for n large enough. Okay, so how do I do this? So again, I can, given this map, I can embed into Kn some Ks, all of which triangle can be filled. Okay, so I start by coloring every triangle of Kn by its homology class, so this gamma should be F. Okay, so every triangle of Kn, I look at, it has some image under F, and I look at the homology class of this image, and this is the color I give to this triangle. Now, what I'm going to do is I'm going to use Ramsey theorem. And Ramsey theorem can provide me with some number of vertices T, so that every triangle on T has the same homology class when mapped through F. Okay? And if I need to make T large, this will only propagate into an assumption that n is large. Okay? So this T can be large as I need it. Then I'm going to start with, say, my triangle, and I'm actually going to map it first to its barycentric subdivision. Okay? Then I'm going to map every vertex in this barycentric subdivision to one of the vertices in T. Okay? Now, this path here, this edge, will be mapped to the edge between, so this one here, for example. Okay, so these are mapped as edge. But of course now the edge here becomes a composition of two edges. Okay? Now, each of these triangle, each of these boundary of triangle will be mapped to some triangle on T, so they will all have the same homology class. Okay, so when I add them up, I get the homology class of this curve. And the homology class of this curve will be trivial because I added 6 triangles. And I'm looking at homology mode 2. And they are all equal. Okay, so that means that now I found a way to PL map this into this so that this triangle can be filled. Okay, and I can do it for here. I can start with KS. I will go to the barycentric subdivision. And if I have enough point in T to map every point of the barycentric subdivision into T, I will have a mapping that makes every cycle in KS fillable, a boundary. Okay? Again, by Ramsey, it's only a question of taking n large enough. Is that okay? Kind of? Okay. And I can do that in any dimension, right? Because every time you take a barycentric subdivision of a simplex in any dimension will be a sum of an even number of simplices. Actually, a sum of a factorial number of simplices. So you will always keep this parity. And so this is a convenient way to make this systematic. It's certainly not economical, right? You could certainly do it with fewer vertices, but that's simple to understand. Okay. Now, with this, now we can go back to Matuszek's theorem, right? Which allowed you to have a constant number of connected components provided each of them is sufficiently connected, and relax that condition that each of them is sufficiently connected into each of them has a bounded number of homology classes. Okay? So we start as before. We take, so for every set we take a point that is missing just that set, and that's the starting of our chain map. Okay, so we're going to build a chain map now, not just an embedding, a map. And now, so we assume that every time you take a subset of large size, there is a pair that is a boundary, right? Simply because you bounded the number of connected components. So we apply the same thing. We find an homogeneous subset T that allows us to draw all those edges. Okay, and this way we build our set. Now, if we have sufficiently many of them, we can fill a triangle. Okay, with this. So, and that will allow us to define the next map. Okay, and there's one issue that we have to be careful about, is that everything, so all of this puts condition on n, which are Ramsey number condition, right? So you want this k to be large enough that you can apply Ramsey theorem, okay? But of course, this t here was large enough that you could apply Ramsey theorem, and so on and so forth. And now, there is one.
N is this final Helly number.
Yes, n is the number of vertices you draw, and every vertex misses one set. So n is the number, both the number of vertices and the number of sets. And the problem is when you're drawing that, you're drawing inside some. So to do this filling lemma here, to do this sequence of reasoning, I'm assuming that this green guy is fixed. That I'm drawing something in a set with a fixed number of homology classes. Okay? And so that means that I'm actually fixing what intersection I'm working in. Okay? And the simplicial complex I want to build should be drawn on, each phase should be drawn in a certain intersection. Okay? So that's one more technical level, and so we need to rework those steps. Okay? And becomes a bit technical. This is just a quick summary of the idea. It's basically you need to insert one more layer of Ramsey that ensures you that how to say it? So basically the set, they define both the vertices and what intersection you are working in. So you need to make some homogeneous choice of families of subsets that will satisfy this position condition. Okay? And so we need to make the injection lemma a bit more systematic, and we basically need to apply Ramsey 3 times. Okay, so I don't think the technical details matter so much. But the idea is that you can really push this idea further and make it work. Okay, so again, the fact that you get bound on Helly numbers from non-embeddability is really not new. That's something you can find. So I think the first published proof of Helly theorem was by Radon, and it used this Radon lemma. Okay, and to find an embeddable structure, you can use Ramsey. Okay, so Ramsey theorem. If you're trying to find a copy of K5 in your graph, that's probably not the best way to go about it. But if you want to have this more systematic way of doing it, if you put constraint on, what are the dummy vertices used by the agent and so on, that's certainly an efficient way a practical way to do it. And then by moving everything into chain maps, you can actually start arguing much more efficiently about cancellation. Okay, and you can make the same relaxation that you did here, not only on the number of connected components, but also on the number of holes of any dimension. Okay. So let me conclude with 2 things. First is some reason why I think this matters. Okay. And may not be obvious when you look at the statement, right? This statement. And the second thing is a few open problems, because I think there are several questions that are interesting. Okay. So what this says is, if you have a family F, and the complexity of the intersection is controlled up to dimension d half, the Helly number is bounded. The function here is horrible. Okay, it's a Ramsey number whose parameters are powers of Ramsey numbers and so on. So why should we care? If you're looking at this kind of problem, so you're trying to minimize a function from Rd to R over some intersection of sets. Okay, I'm not saying that the function is nice in any way. I'm not saying that the sets are nice in any way. Of course, if the function is linear and the set are half spaces, you're doing linear programming. If the function is convex and the set are convex, you're doing convex programming. Okay, quadratic, you're doing quadratic programming. But look at this problem. If under a small generic position assumption, so the local minima of f have distinct values, if you just assume that, or even you could relax this by saying that the number of local minima of f with the same value is bounded. For every value, you have at most 10 local minima of this value. Okay? If this is true, then this problem is what we call GLP. So it's a generalized linear programming problem. That has a very precise consequence, is that you can compute efficiently the minimum provided the Helly number of those family of sets is bounded independently, uniformly. Okay, so what I'm taking is, I'm taking those constraints and I'm looking at the level sets of each constraint, of the constraint with a function. I get a parameterized family of set systems, parameterized by T. And now if I can bound the Haley number of each of those families by some constant that is independent of n, okay, and independent of T also, of course, then there is an efficient algorithm that computes that. What this means is that there is a combinatorial algorithm that will find in linear time a subset of each of these constraints that determines the optimum. Okay, so it doesn't say anything about the numerical complexity of solving the problem. If you go to somebody working in optimization, they will tell you that already convex optimization problem can be very hard because the function can be really wild in a sense. But this is about the combinatorial complexity of the problem is under control as soon as you can prove these bounds. And now a consequence of what I just showed is that for this number not to be bounded, the intersection needs to have arbitrarily large unbounded topological complexity. Okay, so the level sets of the function need to be wild for this problem not to be bounded. Okay, so there are people working in something called complexity theory. Okay, and complexity theorists, they try to understand not what is the complexity of an algorithm, but what is the complexity of the best algorithm for a given problem. So they try to prove lower bound on the complexity of solving problems. Okay, no matter, so they want results that says for any algorithm that solves this, the algorithm takes at least this much time. Now, if your problem can be recast in this way, and there are many that can, and if the level sets of your function behave widely, the best lower bound you can hope will grow linearly in the number of sets. Okay, which is something you can get by just saying you need to read every constraint. Then the number of instructions you need to perform will also grow linearly. So this is an obstruction to proving strong lower bound, or even mildly weak lower bound. Okay. So now a few open problems, perhaps. So what I have in mind when it comes to Haley type theorems of topological flavor that allow disconnection. So there are many, right? We heard of a new one 2 weeks ago. I heard of a new one that Andreas told me 2 weeks ago. So it's not complete, but if you want Haley type theorem with topological assumptions that allow disconnections, there are not so many tools that you can apply. And the ones that I'm aware of are here. Okay, so you get convex sets and you can generalize it to good cover or to R families of good cover, and this was unified by Kalai and Meshulam, who proved that you can also have families that have R pieces of intersection. Okay, and Matuszek kind of systematized this by relaxing the fact that you have a family that is R family over a good cover. And Eekhoff systematized, also generalized this in Eekhoff and Nishke. They generalized it in a more systematic, more axiomatic way. Okay, and what I talked about on Friday is essentially a generalization of this result. So it does not subsume this. And what I told today is essentially a generalization of this result. Okay, that does not subsume this as far as you look at the bounds. Okay, if all you care is that the number is finite, then it contains this result, but otherwise it doesn't. So I think it's a very interesting question to look at whether there is a common generalization of these three results. Okay. Let me add that the lower bound that we get here, that we have here, is very weak. Okay, polynomial in I don't have it in mind, but polynomial in the maximum of the beta I and D. Okay, so that's, I think, one question. There's also a more not philosophical but systematic reason to look at least at the connection between those two. So these results, they come from Neuer theorem, and these results, they come from non-embeddability criteria. And these are two different results in topology, as far as I can tell. And I'm really curious to know whether they have the same strengths or not. Whether what you can get from one, you could also get from the other. There will be some added benefits on just making me happy, because what you get from nerve theorem is proof that the nerve complexes are de-Leray. And this gives you not only Helly theorem, but it also gives you fractional Helly theorem, for example. And epsilon, and it tells you that it's easy to sample the kind of set that you're looking at. And I think one important question is, for example, in this setting, with this assumption, could we have a fractional Helly theorem? A negative answer means those two methods are really different. A positive answer, says maybe we should work harder, and maybe there can be a common proof of all this. Okay. If you look at one of the family of motivating problem I mentioned, that's actually how I got into those problems, is for Helly number for sets of line transversals. So all these results. These results from this result we can get as consequence of the Helly type theorem I mentioned on Friday. If you look at this result, it's actually from 57 due to Adviger. It's of a slightly different flavor. Okay, you see what it tells you is that if you take these joint convex sets in the plane, if any three of them have a line transversal in increasing order, so you require that the line transversal meets the set in a certain order, then they all have a line transversal. And as far as I know, there's no known way to deduce this from the kind of topological theorem I mentioned before. And so in the multinerve argument from Friday, we had this idea that we can control the multinerve, right? The multinerve cannot have boundary of holes. And what we care about was some projection. So we looked at what happens to when we project the multinerve onto the nerve and try to understand how the holes behave. And I think what's hiding behind this question is not projecting the multinerve, but taking a slice. Because each simplex in the multinerve will correspond to a connected component of line transversal. And there are those that satisfy the right ordering condition and those that don't. So you want to remove those that don't, and what will be left will be a subset of the multinerve. So it's not a projection, it's like a section or a pruning in a certain way. Okay, and I believe what is essential in this result is that those guys have, so if you fix the ordering here, you get a single line transversal, you get a single connected component. And so I would assume that although in general you cannot have a Helly type, Adviger type theorem in 3D, I think if you add restriction on the connectivity of the sets of transversals with a given order, and I think that's precisely what this theorem is doing. We're going to unit balls, but in fact, I believe what is crucial in getting the Helly number is that for unit balls, the ordering is the same as the connectivity. Okay, so one question is, could someone please fix those arguments and extend them to encompass this kind of theorem? And a third and last question is that, so if we go back here, if we look at this theorem, and this theorem, they are superficially very different. They are written in different language. So Amenta uses a language of generalized linear programming, LP-type problems, so it's some optimization language. And she proved it this way. Kalai and Meshulam, they use a spectral sequence to end the nerve. And Ekoff and Ishke, they use a purely combinatorial generalized P-journal principle. Okay, so they seem very different. When you read them a bit more carefully, you realize that each of them you can take their proof and use those proofs to prove something that seem very similar in the three cases. In three cases, you can show that when you take two simplicial complex x and y on a map that is surjective, dimension preserving, and with bonded fibers, so each fiber has at most size R, then these maps transport something. So there are various indices on a simplicial complex, which if you can bond it from X, you will get a bond for Y. It can be the Lorentz number, that's what Kalai and Meshulam proved. It can be the Helly number, meaning the dimension of the largest boundary of a simplicial complex that you can find as an embedded subcomplex. Or it can be, not yet. It can be some index, which is basically something called close to what we call the collapsibility of K. It's not exactly the collapsibility of K, but it's basically you have certain filtration of your complex and you're looking at what are the index H, okay, what are the boundary of simplices that are missing at a point, minimally missing, but get filled, okay? And in the three cases, the proof not only gives you the statement that they say about the Helly number, but so not only does it work for nerves of family satisfying your assumption, but it works for any simplicial complexes. And so, could there be a way to unify those three proofs to, show that as soon as you are in this setup, there is a class of functions that behave in this way when you project them, right? You roughly multiply by R. That would be, I think, interesting as well. Okay, thank you.